different shadows that are cast in these IR spectra. The first thing you ever want to do when you come into contact with an IR spectrum is you want to draw a line at 1500. Everything to the right of that line, all of this stuff. You'll notice there are a whole bunch of crazy peaks there. Those are all the single bonds in the molecule. Now, molecules have lots of single bonds, and so this area gets really crazy. The signals merge. It's very hard to read, but it is unique to every molecule, so it's called the fingerprint region. So that just represents all of the single bonds in the molecule. Another useful place to draw a line is at around 3000. Now, you'll very frequently get a dip just to the right of 3000. And that is representing these alkanes. Now notice, it's not exactly on 3000, this is just to the right. These bonds between sp3 hybridized carbons and hydrogens. You have a lot of those in molecules, and that's why you have so many sharp edges there. And it's also why this is so deep. We talked about how light is a wave of electricity, and so what it interacts with in atoms are electric charges in the atoms. And you tend to get that when you have polar bonds, slightly negative, slightly positive. These electric charges would interact with the light. In alkanes, you have a carbon to a hydrogen. It's a tiny, tiny, tiny electronegativity difference. Tiny. This is slightly more electronegative than the hydrogen. But it's really small. We ignore it all the rest of the time because it's negligible. But there are so many in the molecule that they add up, and that's why it absorbs light this well. Okay, so that's what that is here. This, let me do this in a different color. This is sp3 carbon to hydrogen bond. All right, last but not least, we have a smooth bond, a smooth dip between around 3200 here and 3600, and that is an alcohol. That broad smooth dip between 3200 and 3600. So this is an OH bond. So in this question, they're asking in each of the following IR spectra, identify whether what you've got is an alcohol, a carboxylic acid, or neither. Here, we have an alcohol. Okay, we're going to use this little table. We're going to use this again in these other spectra. Now, on a let me actually take a picture of this. On an exam, what you'll want to do is to memorize these. So each of these are something, the shadows cast by each of these different functional groups should be something that you commit to memory, so that when you see a spectrum, you're able to identify the stuff in it right away. Okay, so we'll use that table now as a guide while we're learning. But when you'll know you're ready to, you'll know that you are ready for the test when you're able to identify all the peaks in these spectra without looking at this table or anything like it. Okay, you approach a spectrum, draw a vertical line at around 1500. Everything to the right of that is single bonds. So it's hard to read. Humans can't read it. A computer could compare it to a bunch of spectra in a database and see if it matches any, but it's too complicated for humans to read. It's unique to the molecule, though. That's the fingerprint region. Another useful place to draw a line is at around 3000. Immediately to the right of 3000, like we saw before, is the bond, is an absorption that represents an sp3 hybridized carbon to a hydrogen. So that's a carbon with all single bonds. That's what you'd call an alkane there. You'll notice that we have another peak right here at around 3100. It's splitting into a few pieces, but we have another peak right there. And that, at 3100, is an alkene. That is representing an sp2 hybridized carbon to hydrogen bond. Notice that you have to have a hydrogen on the alkene for that to be absorbed. Okay, we have another thing here. This little peak almost at 1600, that is another bond, but any absorption that is not in this area will not be on a test for you guys. So this table is the place to start, and the other absorptions are things that you wouldn't have to worry about right now. Okay, so this does not have an alcohol, it does not have a carboxylic acid, so this would have neither. Remember, the question for this specific problem was, do you have an alcohol, a carboxylic acid, or neither? In this top one, we had an alcohol. In this one now, we see that we have neither. Okay. In this next one, we have a really broad absorption. It goes a really long way. It goes from starts at around 3600 and it goes to around 2200. That really broad absorption is the first absorption for a carboxylic acid. It's actually the OH bond in a carboxylic acid. This bond right here is vibrating in a different way. It's involved in so many intermolecular forces that it gets spread out. Okay, so basically it's that there. And then you'll notice we have another one. This is 1500 here, 1600, 17, around 1700, we have this next absorption. Oops. So this absorption, that is the carbon to oxygen double bond. So notice at around 1700 you have that for carboxylic acid. So clearly this is going to be a carboxylic acid. Notice a couple other features here. You'd want to always draw that line at around 1500, and notice that everything to the right of that is representing all the crazy single bonds in the molecule. And another small thing to notice is this broad peak is not perfectly smooth. If you draw the other line that we mentioned is useful at around 3000, you'll notice that the sharp part of this peak, it's smooth, 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 finally it gets sharp. The sharp part of the peak is just to the right of 3000. Compare that with what we've seen in the last two spectra. You have those sharp peaks just to the right of 3000. And those are representing single bonds between hydrogen and sp3 hybridized carbons. And so that's what's poking out here. That little area is the absorption from an sp3 hybridized carbon to a hydrogen. It's just overlapping with a much broader, smoother absorption for the alcohol part of the carboxylic acid, the OH. So this is a carboxylic acid. Okay, next one. So you have a new absorption, draw a line at around 1500. Everything to the right of that, single bonds. Those are the shadows being cast by single bonds. Another useful line is around 3000. And immediately to the right of that is the absorption for an alkane. It's just to the right of 3000. And so that's going to be an sp3 hybridized carbon to a hydrogen, casting that shadow. So here we don't have the absorption for an alcohol, which would have been a smooth peak between 3600 and 3200. And we also don't have the peaks that we would see for carboxylic acid, the one at 1700 and the broad one from 2200 to 3600. So this is neither an alcohol nor a carboxylic acid. How about this one? So you see a new IR spectrum, draw a line at 1500. Everything to the right of that is going to represent all the single bonds in the molecule. Overlapping, all their shadows are overlapping and crazy, but they're unique to each molecule, that area. Another useful line to draw is at 3000. Immediately to the right of 3000, we have that absorption, which is for the sp3 hybridized carbon to hydrogen, just to the right of 3000. Oops. Right. And then we have a third peak, this third one right here. It's smooth, and it starts at around 3200, and it goes to around 3600. That is an alcohol. So a broad, smooth dip between 3200 and 3600. That's an oxygen to hydrogen bond from an alcohol. And so what we have here is an alcohol. All right, this one. So we have a new IR spectrum. Draw a line at around 1500, vertical line. Everything to the right of that is are absorptions that belong to single bonds. So those are shadows cast by all the single bonds in the molecule. And then we have two other absorptions. We have this big, fat, broad one. It takes up almost a third of the whole spectrum. And we have this thin, pointy one over here. So this big, fat, broad one extends from around 2200 to around 3600. And that is one of the key absorptions or shadows cast by a carboxylic acid. It's the OH in a carboxylic acid that's casting that shadow. And the other one is the shadow cast at 1700, this right here. That's the carbon to oxygen double bond. So you put those together and you have carbon to oxygen double bond, the OH, that's a carboxylic acid. So that's what we're dealing with here. One of the pieces to note in this molecule, one other thing to note is this little pointy area here. Notice where that is. If you draw our other useful line at 3000, you'll see that that is just to the right of 3000. That's our old friend, the sp3 hybridized carbon to hydrogen bond, which appears in almost every IR spectrum. We've seen it before. It's just peeking out from the smooth OH absorption. All right.